Sounds good.
Okay, welcome everyone to this week's OMR Architecture Meeting. This week we have one topic. It's from John Uman, who'll be talking about Scavenger dynamic breadth first scan ordering in the GC. So take it away, John.
All right. So my name is John Uman. For those that don't know me, I've been IBM Runtime's GC developer for the last 3 years. So today I'm just here to talk about my most recent PR for the Eclipse OMR and Eclipse OpenJ9 project. So this is called Scavenger Dynamic Breadth First Scan Ordering. So just a quick outline of what I'll talk about today. So what is a Scavenger scan ordering? Which, and many of this will be familiar. I'll move through these topics somewhat quickly. But what is dynamic breadth first scan ordering? And for the sake of time, I'll call it DBFSO. So what is the goal of DBFSO? The design and implementation, some results, and then look at the code. So it dictates the order which objects in an object graph are scanned and copied during a GC. So currently within Scavenger, there exists two possible Scavenger scan orderings. We have hierarchical scan ordering, which is the default scan ordering for GenCon, and then we have, which is the default scan ordering, and then we have breadth first scan ordering. So what is dynamic breadth first scan ordering? So it's an optimization for breadth first scan ordering packaged as a new scan ordering. So Scavenger will scan objects breadth first, but dynamic or DBFSO enables the recursive depth copying of hot fields marked by the JIT immediately after the object that Scavenger is currently being copied that contains a hot field. I'm a mouthful, but you'll visually see this and it'll be more clear. So currently it is developed for GenCon, although the first main expected use for it will be in balanced GC, where breadth first scan ordering is still currently the default scan ordering. So what was the goal of DBFSO? So this is to improve BFSO locality issues. So just a brief overview of some basic locality principles. We have the 90-10 rule. So a program spends 90% of the time in 10% of its code. Spatial locality says the items whose addresses are near one another tend to be referenced close together in time. And then we have temporal locality, which states that recently accessed items are likely to be accessed in the near future. So moving on and building on locality, with regards to hot fields and access patterns. So a hot field is a field that is frequently accessed by an object instance. So take a string object. When a field of a string is accessed, typically it's the char array that's accessed. When a hash map node, a field of a hash map node is accessed, typically it's the key or the value. So a hot access pattern is an object access pattern or path that occurs frequently. So hot field information currently is known by the JIT, and there is some information, some usages that we use with this information, but how can we exploit this information and improve locality while scanning and copying objects in Scavenger? So according to the 90-10 rule, if 90% of the time is spent in 10% of the code, there's likely some very hot object access patterns that it would be great if we could exploit. So looking at locality, it would be great if we could have frequently accessed objects beside each other in memory, which will likely reduce cache misses. So take a look at this very basic object graph. So let's say you have object A, which has two fields, B and C. So 10% of the time B is accessed, 90% of the time C is accessed. And if you look at object C, 10% of the time, field F is accessed, 90% of the time, field G is accessed. And then lastly with B, 10% of the time D is accessed, 90% of the time E is accessed. So how can we optimize this object graph for locality? So ideally in memory, it would be great if we could have A, C, and G next to each other and B and E next to each other. So this is how, so looking at this object graph, we'll have, so with root set A and F, and there isn't a step-by-step of how Scavenger would do this, so I don't want to speak about every detail on how Scavenger would approach this this object graph. But from just basically with looking at breadth first scan ordering, what would happen is you'd start with the root set, so A would be scanned and copied, and then F would be scanned and copied, and then scanning A, B would be found, and then as you can see in a breadth first manner, we'll have B, C, D, E, and then F, which has already been copied during root scanning, and then lastly G. But what dynamic breadth first scan ordering will do is while we're looking, so going back to the beginning, looking at the root set, when A is copied, at the end of the copy, we'll ask if A has any hot fields, and it'll say, yes, I have C. So then dynamically, what we'll do is we'll recursively depth copy the hot fields of A. So after A will be copied, then C will be copied. And then, as you would expect during this recursive depth copying, then as C is being copied, at the end of C's copy, it'll be asked, hey, does C have any hot fields yet? And then we'll recurse our way back up, and then looking at the root set after now A is done, so then F would be copied. And then we'll move to, so while after A is scanned, we'll have B, and then while B is being copied, at the end, I think you understand where I'm going. After B is copied, at the end of the copy, it'll ask, hey, do I have any hot fields? Yes, you have E. So then E would be copied next, and then B would be scanned, and D would be found, and it would continue in a breadth first manner anytime that there isn't going to dynamically adjust for the hot fields. So just some basic takeaways of DBFSO is that it enables the possibility to have to memory, and it will likely result in fewer cache misses. So at a high level, looking at the design and implementation, there is leveraging of existing information that's done. So applications consist of compilation instances, and the JIT compiler is a tiered compilation compiler, meaning that each method starts at a base compilation level, and then the JIT can decide to optimize a method further based on various heuristics that relate to how frequently a method is being run. So looking at the test roasted compilation levels, we have cold, warm, hot, very hot, and scorching. So each compilation is divided into code blocks where the relative hotness of each block within the compilation is determined, and blocks receive a normalized hotness value for all purposes, I'll say between 1 and 10,000. So when a field is accessed within the compilation, we use, so this is an optimization pass that was implemented by Andrew Kreck, who I believe is on the call right now. And so we can use this compilation level of the method as well as the block hotness of the block within the compilation where the field was accessed to compute an overall hotness value for the particular field within the compilation. So this hotness value is computed for every access and every compilation for each field of a class. And so once again, this is also done as a compilation is promoted or optimized. So for each field of a class, we can aggregate these hotness values for the field accesses across all method compilations and get an approximate value for the hotness of each field of a class. So now, knowing the approximate relative hotness of each field of a class, during a GC, when an object survives the GC and is copied to the survivor space, we will recursively depth copy the two hottest fields directly after the object itself is copied during a scavenge. So if I look at, and so we'll look at some of the code shortly, but if we look at results, and there's more performance benchmarks that have been run, but if we look at ones initially right now for SpecJBB 2005 and SpecJBB 2015. So these were runs consistent throughout the development of the feature, but I gathered new ones just for the sake of having clear-cut results of what it is looking at like right now. So we look at SpecJBB 2005 with breadth first scan ordering, and you do a throughput comparison. You see that this dynamic breadth first comes up just about 7.5% ahead. And then if we look at SpecJBB 2015, if we look at SpecJBB 2015, we'll see that for max JOPS, we'll have almost a 4.5% improvement. And then for critical JOPS, roughly a 2% improvement. So with regards to getting into the code, I wasn't entirely sure on the best way to do it, but I have links right here to the pull request for the Eclipse OMR and Eclipse OpenJ9 projects, as well as some details where the more important aspects of the code can be found. And then I also have a touch or just a slide summarizing some of the key data structures that are used within this feature. So that for the presentation, that would be all. But Daryl, is there any way or any do you know how you would like to move forward with looking at some of the code, or perhaps talking about some of the design?
Well, I guess we can just pause here and see if there's any questions about what you've talked about. I mean, if you want, you can certainly dive into take people through a more structured walkthrough of the code. I know myself, I have a question about something you talked about on slide 11, which was you talked about aggregating. Let's read it here. You come up with an aggregation of all these different hotness values. How do you do that aggregate? How is that aggregation done? Is it an average?
That average, there's a few different reduction algorithms I've been playing around with, but yes, an average would be one of them. I've also done an average, a summation, and I did implement also like a minimum and a maximum, but for the sake of the initial commit, I left those out in a private branch. But yes, that's correct. So these are averaged among combination blocks.
Is the hotness of the method itself part of that aggregation? I know you do the block frequencies, but how about the actual method itself?
So the aggregation is regards to the block frequencies solely, but if you look at the information that's stored with regards to the field after we've aggregated this block frequency, what we do is similar to what was implemented before in the old hot field implementation, is we'll multiply this value by a factor. So as of now, it's more or less copied directly from from what used to happen before for hot fields. So for a warm compilation, this value, this aggregated block frequency value is multiplied by 1. For a hot method, this aggregated value is multiplied by 10. And for a scorching method, this aggregated value is multiplied by 100. That has been looked into to potentially, for a next phase of this, to look into try to getting CPU utilization for each 4 methods that will allow in a far greater increased, or a greater increased accuracy to this, as methods of the same compilation level will differ, can differ somewhat significantly. And especially in applications as day trader, there'll be minimal benefits as methods. So so it won't have a major effect in applications like that. So that would be a next step.
Okay. How is the? I seem to recall that that you created a pull request several months ago for this, and there was some discussion around how the hotness information was communicated from the JIT to the GC. I don't remember what the resolution of that was. How is the hotness information exchanged with the GC?
So the hotness information is stored within. So the hotness information, I think this slide might help a little bit. So it's stored in. So each class loader is currently now, and so I'll back up a step and just say that for most, for all VM decisions, I would, for all the VM decisions, Toby was my go-to for expertise, and then for all JIT related questions, Andrew Kreck was my go-to, and then for GC, Alex Micic was, when it came to architecture, was the ones I contacted. So looking at this, so this was the best decisions that we collectively came up with. And so looking at a J9 class loader, so this is from speaking with Toby, we came up with each class loader will have a hot field pool. And so this will have a pool for all hot fields related to all classes for that class loader. And then we'll have a global pool of what we've called J9 hot class info. So we'll have a global pool of these objects. And so each class has an initially null hot fields info, and then as its first hot fields are discovered, we'll initialize this pool element. So this would be a global pool, and so how this information is then, information is stored in these data structures, and then at the beginning of a GC, what we'll do is we'll go through the J9 hot fields info pool, and then now we know we only store the head of the list, so we'll iterate. We'll go through all these objects, and then so as you can see, the hot field list head just points to the head of the list within the hot field pool of the class loader. So what we'll do is it will iterate this list, and we'll find our two greatest hot field, the two greatest hotness values. We'll then store these in our hot field offsets, and then when Scavenger is copying, it'll ask for yes, that's correct. Sorry, when Scavenger is copying, it'll ask for the first hot field offset and the second hot field offset, and then based off that, we'll recursively depth copy the hot field. And then there's a special value of U8 a U8 max that lets Scavenger know that currently doesn't exist a hot field there. So this previous, and then so I guess working just a little bit back to your initial question regarding the issues of first implementation together with that was reworked together with Andrew's guidance, who I believe if Andrew wants to elaborate anymore, but I believe that I should cover that. Does that make sense?
Yeah, okay, interesting. Yeah.
I have a question.
Okay.
Feature. So as my understanding goes, looks like this hot field is like a static to every class instance, meaning if there is a new instance of this class, all the hot fields are inherited from whatever values they were previously. So what would be the difference between like a class that has 2-3 fields and another class that has 8, 9, 10 fields? So how would these structures behave in those scenarios?
So as of now, there's a hot field max capped off at that list length is capped off at 10, but there's also a certain threshold that during the hot marking pass, there's a certain threshold of block frequency that has to be met in order for that field information to be stored, and that's to avoid the possibility of having excessive amounts of hot fields. So for each new object, that's created, it will inherit the hot field offset instead of being already set. Does that answer the question?
Yeah, definitely. Awesome. Thanks.
No problem. Does that make sense? Are there any other questions or?
What is the what is the state of the pull request in OMR? Sorry, I guess I can bring that up, but what are there issues outstanding that need to get addressed, or is it just needing a review?
As of now, it's just needing it would be just needing a review. So there's been some preliminary reviews before this, but as of now, it is I would say more or less ready. It is ready for review.
Okay. Is the hotness information preserved in the shared classes cache?
No, sorry. Actually, let me think about that. The hotness.
So when we, yeah, I mean, so that we can use it on the next invocation.
I believe so. Yes, it would be kept. I don't see why it would not. I believe so. Yes.
Okay. Okay. Other questions for John? Okay. So I don't know if you said that you were maybe prepared to take people through a code. I mean, I think that would help if for those that are going to be doing the review. I'm not unless people really want that level of detail. I don't know if we need to go that deep. But if somebody does want John to do that, by all means, please speak up. Okay. If not, I think that was a good design. Thanks for taking us through that.
No problem.
Okay. Last call for questions. Otherwise, that's all that we had on the agenda for today. So I guess we'll adjourn if there's.
Just one last question, or one question. How consistent are you finding the results from this from run to run? Like, because there's a certain aspect of this that depends on compiles that happen earlier sort of influence compiles that happen later, and there's some non-determinism in the order in which compiles happen anyway. So
Right.
overall, does it all sort of become a wash and you get fairly consistent results from run to run? That was what I was curious about.
Yes. That was I would say overall that was one of the things that was for sure an initial concern. But overall, I can I guess I could no I'll leave out some other results. So I'll have to it might be a little difficult to find. But overall, every quite consistent, very consistent values, and each one looking back at the analysis that I did, and this is I'm just trying to remember, but each run had, so if you look at, for example these results, each one would have had roughly a within 1 to 2% of the value. So if you look at the percent improvement, sometimes it varied between let's say 6 and 8 or 7 and 9. And if you look at the improvements for spec with regards to max JOPS and critical JOPS, they tended to be very, very within a margin, within a thin margin. And so along with this, like compile time, like Quarkus, footprint, throughput, compile time, and all that was analyzed, and all those have shown very consistent values.
Okay, yeah, I was thinking more in terms of just from a if run 1 said that field 1 and field 5 were hot, is that sort of consistent from run to run for the same class? I guess is what I was thinking of. I guess the perf results are a proxy for that field information being fairly consistent.
But actually, sorry, I can better answer that question then. Yes, I had the exact same questions myself while I was doing it. So this would be slightly, perhaps, a month dated. But at several points, I did perform an analysis on all the fields, all their hotness values from run to run, and the overall 2 hottest fields. And so that's I think from run to run, there's some variance among the ordering of the hotness of the fields, but when it came down to the two hottest fields, those were consistent every time with the benchmarks I looked at. Does that make sense? So the 2 hottest fields that will actually be recursively depth copied, those were consistent every time for every run.
So with the analysis that you did to validate that, did you find that there were some classes that had more than 2 fields that might benefit from this kind of locality?
Yes, I did. I found some, and I found some that had let's say some that had 3 to 4. 3 to 4 hot fields, but then some with so I think there's room. I really believe there's room for plenty more optimizations to this moving forward. But yes, there were some that had at least 3 that were quite hot fields.
So I guess the trade-off would be the added footprint cost of storing that frequency information for a couple of extra fields. I don't know, it just might be useful or interesting from just to see what kind of performance you can get perspective if you just increase the size there and sort of see how it affects some of these workloads that you're running. You capture more than just 2 fields.
Yeah, that for sure would be a possibility. I know with regards to I'm not sure how wide the benefits would be just with regards to looking at like if you look at, let's say, this this object graph, and now let's say that both B and C were hot fields. So let's say we're now in this scenario, we're keeping 2 hot fields. So if we're copying to a depth of, so I have a depth set to 3, so it'll copy a max depth of 3. But within that, if you're copying to a depth of 3 for 2 hot fields, if you go along this path, I believe that even if you extend that to a 3rd hot field, outside of the cache line anyway. So I'm not sure if those benefits would be inherited from extending further. That was my thought, because I had thought that when I saw some results that had 3 or a 3rd hot field. Does that make sense?
Yeah. And maybe the other thing that I was wondering is, I imagine that the frequency information that gets computed, is that recalibrated as the application is running? So if you pick fields D and E, at some point later on, it might change to E and X or something like that. And
yes,
you would
correct.
reflect that in the, okay.
So there's an adaptive sorting that takes place. So within the first, so I have it now. I experiment with some of the different values. So now for the first 200 scavenges, on each scavenge, a quick a sorting of the hot fields takes place, and that will allow for the adaptability of hot fields. And then moving forward for the rest of the duration, I can't quite remember the value, but every X amount of GCs, we increment that adaptive sorting. So for example, on GC 1000, let's say, you're sorting every 6, 7 GCs. And that was done from looking at various benchmark runs, that as life went longer and longer for the program, there wasn't much need to continue to sort every GC.
I see. Cool. Right. All right. Anything else for John? Okay. All right. Well, thanks, John, for preparing that and taking us through that. Hopefully, we can get that reviewed and merged in short time.
Excellent. No problem.
Yeah. Okay. Well, that's all that we had on the agenda for today. So thanks everyone for attending, and we'll meet again in 2 weeks. Okay. Thanks. Bye.
Thank you. Bye-bye.